There is a particular kind of darkness that belongs only to the Mojave Desert in the final hour before sunrise. It is not the dramatic darkness of a storm or the soft darkness of a forest at night. It is something older than both of those. It is a stillness so complete, so absolute, that the very air seems to hold its breath. The stars above are fierce and countless, scattered across a sky so clear it almost hurts to look at, and on the ground below nothing moves, not a branch, not a leaf. Not even the faintest whisper of sand. The cold settles into the desert floor before dawn in a way that surprises most people who have never stood here. They expect heat, always heat, because the Mojave is famous for it. But in these quiet hours before the sun reclaims the day, the temperature can drop into the 40s, sometimes lower. A cold that has nowhere to hide from, no trees to press yourself against, no wall to shelter behind. Just the open valley floor stretching away in every direction, and the slow, patient darkness above. Before we go any further, please consider leaving a like on this video and subscribing to History Sleepy Time so these journeys keep finding their way to you. And drop a comment below telling us where in the world you are watching from tonight. We genuinely love hearing from you. Now, let us go back to that quiet Mojave morning, scattered across that valley floor. Volcanic hills rise in dark silhouettes against the paling sky. They look almost like sleeping animals. Their slopes are rough and broken, piled with jagged basalt and crumbling cinder, and in the weakening darkness they seem to float, half present, somewhere between the real world and whatever place the desert becomes at night. The ground itself is a patchwork of pale sand, broken gravel, clusters of creosote bush, and stretches of sun-bleached hardpan. Dry washes cut shallow channels through the desert floor, carved by water that has not run here in years, sometimes decades. The Joshua trees stand at irregular intervals, their twisted arms reaching in directions that seem to follow no plan, as if each one decided independently how to grow and simply refused to consult the others. This is the Mojave, one of the most testing landscapes on the North American continent. It covers roughly 47,000 square miles across parts of California, Nevada, Utah, and Arizona. It is classified as a high desert, sitting at elevations that range from below sea level near Death Valley to more than 5,000 feet along its mountain edges. The temperature swings across a single day can exceed 50 degrees. Rain, when it comes at all, may deliver the entire year's moisture in a single violent afternoon. The rest of the time, the sky stays empty and the ground stays dry, baking slowly under a sun that seems, at its peak, to push down with physical weight. And yet people have always come here. They have crossed it on foot, on horseback, by wagon, train, and automobile. They have suffered here and endured here and occasionally found remarkable things here. The surface of the Mojave is itself a kind of puzzle, layered with geology and history and memory in ways that take time to read. But there is another landscape beneath this one. A landscape that most people have never seen and may never think about, even as they drive across the desert on a summer afternoon with the air conditioning running and the windows rolled up against the heat. Beneath the sand and the hardpan and the broken volcanic rock, beneath the dry washes and the scattered springs and the ancient lake beds, another world has been forming. Slowly, quietly, over millions of years, shaped by forces that work on timescales the human mind finds genuinely difficult to hold. Water and fire and pressure and time have been building something vast down there, something intricate and strange and mostly still unknown. If the Mojave has always tested those who crossed its surface, what hidden world has been quietly growing beneath it? The question does not arrive with any fanfare. It just settles, the way the cold settles before dawn, gently and completely. At the base of one of those dark volcanic hills, where the rock has fractured along some ancient line of stress, there is a narrow fissure in the stone. It is easy to miss in daylight, half concealed by a fall of broken basalt and a single stubborn clump of desert holly. But if you stand near it in this pre-dawn quiet, you will notice something unusual. Cool air is rising from it, not wind. Not any movement of the atmosphere above. Something moving upward from below, from somewhere deep in the rock, air that carries a faint mineral scent, something ancient and clean, the smell of stone that has never been warmed by any sun. The darkness below the fissure is complete. The rock narrows and drops away into nothing visible. Whatever is down there is patient and still, and for now entirely its own. That is where we are going. To understand what lies beneath the Mojave, you have to begin with a story that started roughly 30 million years ago, deep inside the Earth itself. The western portion of the North American continent sits within a geological region known as the Basin and Range Province. It is an enormous area, stretching from southern Oregon down through Nevada, across most of the American Southwest, and into northern Mexico. What defines this region, what gives it its name and its character, is a process of crustal extension that has been slowly pulling the continent apart. Think of it this way. The tectonic forces operating beneath this part of North America have been stretching the crust, as if it were a piece of dough being pulled gently in opposite directions. As that crust stretches, it does not thin smoothly. Instead, it breaks along fault lines, and the blocks between those faults either rise or fall. The blocks that rise become mountain ranges. The blocks that drop become basins, the flat valley floors that sit between those ranges. This is why, if you fly over the Mojave or study it on a topographic map, you see that striking pattern of parallel mountain ranges separated by broad, flat valleys. The ranges run roughly north to south, ridge after ridge, separated by basins that were once far deeper than they appear today. Basins that have gradually filled with sediment washed down from the surrounding mountains over millions of years. The faulting that created this landscape did more than shape the surface. It fractured the rock throughout the region, creating networks of cracks and fissures that run deep into the earth. Along some of these fault zones, the rock has been shattered and displaced over and over again through millions of years of seismic activity. These fractured zones become pathways, channels through which water can move, through which air can circulate, through which the slow dissolution of certain rock types can hollow out chambers and passages that no human being has ever entered. The volcanic history of the Mojave adds another layer of complexity to all of this. Volcanic activity in the region is not ancient history in a purely distant sense. The Mojave contains dozens of volcanic fields, areas where basaltic magma has erupted through the surface at various points over the past several million years. The Cima volcanic field in the eastern Mojave, for example, contains more than 40 individual cinder cones and covers an area of about 54 square miles. Most of its eruptions occurred within the last 800,000 years, and some of the most recent flows are estimated to be only 10,000 years old, a geological eye blink. When basaltic lava flows across the surface, it behaves in a specific and rather remarkable way. The outer surface of a lava flow, exposed to air, cools and solidifies relatively quickly, but the interior of the flow continues moving, sometimes for considerable distances, carried forward by new lava pushing from behind. When that interior lava eventually drains away or cools and contracts, it leaves behind a hollow tube, a passage through solid rock, sealed on all sides by the hardened outer shell of the original flow. These are lava tubes, and they occur throughout the volcanic regions of the Mojave. Some of them are modest, narrow passages just large enough to crawl through. Others are genuinely large, with ceilings high enough to stand comfortably beneath and widths of 20, 30, even 50 feet or more. The walls of these tubes often preserve remarkable textures. You can see the high water marks of lava flows frozen in stone, horizontal shelves called lava benches, where the level of moving lava once stood. You can see the ceiling covered in smooth, rounded protrusions called lavasicles, formed by the dripping of cooling rock. You can find mineral deposits along the floors and walls where groundwater has slowly worked its way through over thousands of years since the tubes were formed. Below the volcanic layers, the geology becomes even more varied. Scattered across the Mojave and its surrounding ranges are outcroppings of limestone and dolomite, carbonate rocks that have a special relationship with slightly acidic water. When rainwater absorbs carbon dioxide from the atmosphere and the soil, it becomes weakly carbonic, just acidic enough to slowly dissolve limestone over long periods. This process, called karstification, can hollow out remarkable cave systems from solid rock, creating chambers, passages, and sinkholes collectively known as karst topography. The karst features of the Mojave region are not as dramatic or as widely documented as those of more humid regions like Kentucky or the Yucatan Peninsula. Karst formation requires water, and the Mojave does not have much. But over sufficient time, even the Mojave's modest rainfall, combined with the ancient wetter climates that characterized the region during the Pleistocene ice ages, has been enough to create cave systems in certain limestone formations throughout the desert. The Pleistocene epoch, which lasted from roughly 2.6 million years ago until about 11,000 years ago, was a critical period for the underground development of the Mojave. During that time, the region was considerably wetter and cooler than it is today. Lakes filled the basins that are now dry. Rivers ran across the surface where only dry washes exist now. Groundwater tables stood much higher, saturating rock formations and actively dissolving limestone, enlarging fractures in volcanic rock, and depositing minerals in patterns that still speak to us today about a very different desert than the one we see on the surface. As the climate shifted and dried, those ancient water tables dropped. The caves and passages that had formed in saturated rock were left behind, their chambers now filled with air rather than water, their walls decorated with the mineral formations that precipitating groundwater left as it slowly retreated. What remained was an underground landscape of extraordinary complexity, formed across millions of years by the combined work of volcanic activity, tectonic fracturing, chemical dissolution, and the patient movement of water through stone. And most of it has never been explored. Geologists and speleologists, the scientists who study caves, have surveyed portions of the Mojave's underground. They have mapped individual lava tubes, documented karst features in the limestone ranges, measured groundwater levels in the deep aquifers that still lie beneath the desert floor. But the scale of the region, the harshness of the access conditions the danger of unstable volcanic tubes and collapsed mine workings, and the sheer number of features that remain unexamined means that every survey, every expedition, every carefully documented cave adds only a small piece to an immense and mostly unknown picture. The Mojave built itself underground across a timescale that makes human history seem like a brief and recent development, and it built something genuinely vast. The surface you see from a car window or a viewpoint or an airplane is only the thinnest possible introduction to what this desert actually is. Beneath that surface, cool air moves through passages no light has ever entered. Mineral formations grow at rates measured in fractions of a millimeter per century. Water, where it still exists underground, moves through aquifer rock so slowly that a single drop of rain falling on the surface today may not reach the deep water table for thousands of years. This is the foundation of everything that follows. The stone itself, fractured and dissolved and reshaped across unimaginable time. Everything else, every person who has ever crossed this desert, every culture that has lived here, every miner who has swung a pick into its rock walls, has done so against this backdrop of geological deep time. The desert does not notice. It simply continues, slowly and inevitably, building its hidden world below. There is a particular kind of spring that appears in desert landscapes without warning. You are walking across open ground, cracked hardpan stretching away in every direction, not a trace of moisture anywhere, and then quite suddenly the air changes. There is a coolness to it, a faint green smell. And a moment later, you see a cluster of willows and cottonwoods growing in a tight group around a seep in the rock, a place where water traveling through underground pathways that may extend for many miles finally finds its way to the surface. These springs are not anomalies in the Mojave. They are expressions of a hydrological system of extraordinary age and complexity, a system that, in many ways, was the original architect of the underground world we have been exploring. Water has a way of going where you do not expect it. In a desert environment, the relationship between rainfall and groundwater is not simple or direct. When rain falls on the Mojave, which it does, particularly in the form of winter frontal storms and summer monsoon events, it does not simply evaporate or run off into nearby drainages. A portion of it is absorbed into the soil and begins a long, slow journey downward through layers of gravel, sand, fractured rock, and eventually into the porous formations of the deep aquifer system below. The Mojave Basin and its surrounding ranges sit above a complex network of groundwater systems. Some shallow and relatively responsive to modern rainfall, others so deep and so old that the water held within them fell as rain not during any modern weather pattern, but during the wetter climates of the Pleistocene tens of thousands of years ago. This ancient groundwater, sometimes called fossil water, has been stored in the rock since a time when mammoths and giant ground sloths walked the shores of lakes that are now bone-dry playas. Those ancient lakes matter enormously to this story. During the Ice Ages, the Mojave region contained a series of large pluvial lakes formed by increased precipitation and reduced evaporation in a cooler climate. Lake Mojave occupied what is now the dry bed of Silver Lake and Soda Lake. Lake Mannix sat near present-day Barstow. Further north, the Owens River system carried water southward through a chain of lakes that filled basin after basin in a connected system that hydrologists have gradually pieced together from geological evidence. When those lakes were full, the groundwater table throughout the region stood at levels that modern residents of the Mojave would find almost unrecognizable. Water percolated into the limestone formations of the mountain ranges surrounding the basins, dissolving rock and enlarging existing fractures into something approaching true cave passages. Water flowed through the fractured basalt of the volcanic fields, depositing minerals, washing away debris, leaving behind smoothed and shaped passages that still exist today within those lava tubes. Flash flooding, that sudden and dramatic feature of desert hydrology, also played a role in shaping the underground. During periods of heavy rainfall, dry washes carry extraordinary volumes of water, sometimes within minutes of the first drops falling miles away in the mountains. That water moves with tremendous force, carrying sand, gravel, and larger rock fragments that act as tools of erosion. Where a wash crosses a fractured zone in the bedrock, or where water finds a path downward through a collapse or a fissure, it can begin carving a route underground, washing out material and leaving a passage behind. The process is not quick by human standards. But the desert has been doing this for a very long time. Some of the cave systems in the eastern Mojave region, in the limestone ranges near what is now Mojave National Preserve, were shaped in part by exactly this kind of process. Water working its way downward through carbonate rock, dissolving and transporting material, sometimes over hundreds of thousands of years, sometimes in relatively sudden episodes during particularly wet periods, created passages and chambers that stand today as evidence of a very different hydrological regime. The dry lake beds, or playas, that now dominate many of the Mojave's valleys are themselves a kind of geological record. The sediment layers within them preserve the story of alternating wet and dry periods, a climatic history written in clay and silt, and occasional lake shoreline features still visible as faint lines on the slopes above the basin floors. Reading those layers tells scientists not just about ancient water levels, but about the timing of cave formation, groundwater movement, and the gradual drying that has characterized the past 11,000 years of Mojave climate. Groundwater continues to move through the Mojave today, though more slowly and in smaller quantities than during the wetter periods of the past. The springs that appear at the base of mountain ranges are expressions of this movement, places where the underground water system intersects the surface through fault zones or permeable rock layers. Amboy Crater in the eastern Mojave, Devil's Playground, the vicinity of 29 Palms and its oasis. All of these surface features are connected to an underground hydrological network that extends far beyond what is visible at the surface. Geologists and hydrogeologists studying the region have, over the past several decades, developed an increasingly detailed picture of how this underground water system works. Isotopic analysis of water samples from springs and wells can reveal the age of the water, where it originally fell as precipitation, and the general path it has taken through the rock. Some of the water emerging from springs in the Mojave today is measurably ancient, recharged during the wetter climates of the past, rather than by any modern rainfall. This means that somewhere underground, in rock formations that have not been directly examined by any scientist, water that fell as rain during the Pleistocene is still moving through passages shaped by forces that were active long before any human being set foot in this desert. Could the greatest architect beneath the Mojave have always been water rather than sand? The question settles into the narrative here because the answer, as far as the evidence suggests, is probably yes. Sand moves on the surface, shaping dunes and filling washes, but it is the work of water, patient and persistent, moving through rock over geological time, that has created the deepest and most complex features of the underground Mojave. Fire built the tubes, faulting created the fractures. But water, working with chemistry and time, hollowed out the chambers, smoothed the passages, deposited the mineral formations, and left behind the caves that now sit in cool darkness beneath the desert floor. The water did not finish its work and leave. It is still here, moving slowly through stone, finding new paths, dissolving rock grain by grain in amounts too small to measure on any human timescale. The desert above is dry. The desert below has never entirely lost its water. And the underground passages that water shaped, long before any human being thought to explore them, were already waiting when the first people arrived in the Mojave, which, as it turns out, was a very long time ago indeed. Long before the first wagon wheel cut a track across the Mojave, long before the first prospector knelt beside a dry wash and lifted a pan of gravel toward the light, human beings were already here. They had been here for a very long time. The archaeological evidence for early human presence in the Mojave Desert extends back at least 13,000 years, and possibly considerably further, into a period that archaeologists refer to as the Paleo-Indian era. These were the first inhabitants of North America. People who had moved southward and eastward from northwestern pathways as the great ice sheets of the Pleistocene began their slow retreat following animals and plant resources into landscapes that were opening up for the first time in tens of thousands of years. The Mojave that those earliest people encountered was not the desert we know today. It was a wetter, cooler, more generously vegetated landscape. The lakes we mentioned in the previous chapter were still present or only recently retreated. Grasslands extended across areas that are now creosote flats. The mountain ranges surrounding the basins supported forests at elevations that today grow only sparse scrub. And across this more hospitable landscape, a different community of animals moved, animals that no longer exist anywhere on Earth. Mammoths had lived in the region, mastodons. Giant ground sloths that stood taller than modern grizzly bears. Camels and horses, which are native to North America despite what most people assume, having evolved here before spreading to other continents. American lions and dire wolves and the short-faced bear, a creature of remarkable size that could, when standing, reach heights that made it the largest terrestrial mammalian predator North America has ever seen. The Paleo-Indian peoples of the Mojave hunted some of these animals, or at minimum shared a landscape with them. Their tools, the finely crafted stone projectile points that archaeologists identify as the signature of these early cultures, have been found at sites throughout the Mojave region. The Clovis culture, identified by a distinctive fluted point style, represents one of the earliest and most widespread of these traditions, with evidence dating to roughly 13,000 years ago. Later traditions, including what archaeologists call the Folsom culture, and a variety of regional point styles that followed, extended through the subsequent millennia as both climate and the human cultures adapted together. What is striking about the archaeology of this period in the Mojave is not just what has been found, but where it has been found, and what that tells us about how these early peoples moved through and understood the landscape. Rock shelters, natural alcoves formed in cliff faces and canyon walls, where overhanging stone provides protection from weather, were used as temporary camps and shelters throughout the region. Some of these shelters show evidence of repeated use over thousands of years. Layers of ash from fires, fragments of bone and shell and worked stone, accumulated in deposits that archaeologists read like pages in a very slow book. The shelters themselves were not permanent homes, but seasonal stopping points along routes that early peoples followed as they tracked animal migrations, followed plant ripening cycles, and moved between water sources. Water sources were inevitably the organizing principle of movement across this landscape. Springs, seeps, the remnants of lake shores, seasonal streams, and the reliable sections of larger drainages. These were the anchors around which everything else was arranged. Routes between water sources became established paths, followed season after season, generation after generation, until they were less individual choices than inherited knowledge, the accumulated navigational wisdom of a people who understood this landscape with a depth and precision that comes only from living within it across many lifetimes. Among the most important materials in the Paleo-Indian toolkit was obsidian, the volcanic glass that forms when silica-rich lava cools rapidly. Obsidian fractures with extraordinary precision, producing edges sharper than surgical steel, and Paleo-Indian craftspeople used it to make projectile points, cutting tools, and scrapers of remarkable quality. But obsidian does not occur everywhere. It is found at specific volcanic source locations, and a piece of obsidian found at an archaeological site can often be traced back to its specific origin point through chemical analysis. a technique called X-ray fluorescence sourcing. The obsidian trade networks that operated across the Mojave region during the Paleo-Indian period and into the subsequent Archaic period are revealed through exactly this kind of analysis. Obsidian from sources in the Coso Range of eastern California, for example, has been found at sites hundreds of miles away. Material from sources in Nevada and Oregon appears at sites in the Mojave. This movement of material across vast distances tells us that these were not isolated groups of people making their way blindly through an unknown landscape. They were participants in networks of exchange and communication that connected communities across much of Western North America. The stone itself became a carrier of connection, moving hand to hand and camp to camp across a landscape that to those who knew it was not empty or hostile, but readable and inhabited, full of meaning at every spring and canyon and painted cliff face. Rock art, the petroglyphs pecked into the desert varnish of boulders and canyon walls throughout the Mojave, represents another form of that inhabitation. The Great Basin and Mojave regions contain some of the most extensive and varied rock art traditions in North America. Bighorn sheep appear frequently, along with human and geometric figures, patterns of dots and lines and spirals whose meaning is not always recoverable, but whose presence speaks clearly to the fact that these were landscapes marked and remembered and returned to. Some petroglyph sites in the Mojave are associated with springs or reliable water sources, suggesting that these places held particular significance in the geography of movement and memory. Others appear along what researchers have identified as likely travel corridors, routes through mountain passes, and along valley floors that connected one water source to another and one community to another across the desert. It is important to be careful here about the language we use. Archaeology gives us evidence of behavior, of movement and material culture and subsistence patterns. It is more cautious about interpreting meaning, about saying with certainty what a particular site meant to the people who used it, or what beliefs and understandings shaped their choices. The archaeological record of the Mojave is rich and continues to grow as new sites are documented and existing sites are studied with newer methods. But it is also fragmentary, shaped by what was preserved, what has been found, and what research has been funded and undertaken. What we can say with confidence is this. When the first Euro-American explorers crossed the Mojave in the early 19th century, they were moving through a landscape that had been continuously inhabited, seasonally traversed, and carefully known by human beings for at least 13,000 years. The land they described as empty and unknown was neither of those things. It was a landscape dense with human history, most of it simply invisible to eyes that did not know how to read it. The distinction between that ancient, deeply known landscape and the desert that later arrivals perceived as a blank and forbidding wilderness is one of the central ironies of Mojave history. And it is worth holding onto as we move forward into the living traditions of the peoples who called this place home when the prospectors and the surveyors and the railroad engineers arrived. To speak carefully and respectfully about the indigenous peoples of the Mojave Desert is to begin by acknowledging something that is easy to overlook. This is not one story. It is several stories belonging to several distinct nations, each with their own language, their own territory, their own history, and their own relationship to the desert landscape they inhabited. The Mojave people, who call themselves Pipa Aha Makav, meaning the people who live along the river, are traditionally associated with the lower Colorado River Valley and the broader Colorado River corridor. Their territory extended westward into the desert proper, and they were known as skilled long-distance travelers, journeying on foot across hundreds of miles of desert to trade and to maintain relationships with peoples in California's coast and interior valleys. The Mojave were agricultural people in their river homeland, growing corn, beans, and squash in the floodplain, but they moved through and intimately knew the desert that surrounded that homeland. The Chemehuevi, whose traditional territory covered a large portion of the central and eastern Mojave, were among the most accomplished desert travelers of any people in the American Southwest. Their deep knowledge of water sources, travel routes, and desert resources allowed small family groups to move across an enormous range, following the seasonal availability of food and water with a precision that speaks to generations of accumulated ecological knowledge. The Chemehuevi are Southern Paiute people, linguistically and culturally related to other Paiute groups to the north and east, and their traditional territory overlapped and adjoined those of their neighbors in complex ways shaped by long history. The Southern Paiute peoples more broadly occupied a vast region stretching from the Mojave Desert northward into Nevada and Utah. Like the Chemehuevi, they were largely mobile desert peoples, with a profound knowledge of plant resources, water locations, and seasonal movement patterns. Their relationship to the landscape was one of intimate familiarity built across countless generations, a familiarity encoded in place names, in stories, in the knowledge of which plants grew near which springs and which passes could be crossed in winter. In the western and southwestern portions of the Mojave Desert and its transitional zones toward the mountains, the Serrano and Cahuilla peoples maintained their own distinct territories and traditions. The Serrano, whose name derives from a Spanish word meaning highlanders, occupied territories in the mountain ranges bordering the Mojave, including the San Bernardino Mountains, with seasonal movement into the desert itself. The Cahuilla, a linguistically Ute-Aztecan people, held territories in the mountains and desert areas of what is now Riverside and San Diego counties, including portions of the Coachella Valley and the desert ranges to the east and northeast. Each of these nations maintained its own traditions, its own ceremonial life, and its own body of knowledge about the landscape they inhabited. To speak about them as a single category, as simply the desert peoples, would be to flatten distinctions that were meaningful and important to the people themselves, and that remain meaningful and important today, because these are not historical peoples. They are living communities with descendants, with continuing cultural practices, and with relationships to their ancestral landscapes that did not end with the arrival of Euro-American settlers. With that grounding clearly in place, we can speak in general terms about some of the themes that appear in the relationships between these various nations and the underground world of the Mojave, while being careful to note that specific traditions, meanings, and practices belong to specific communities and should not be homogenized or appropriated. Springs held particular significance across the desert Southwest. In a landscape where water was the organizing principle of life, the places where water emerged from underground were not simply practical resources. They were places of power and meaning, points where the underground world made contact with the surface world, where something that moved hidden through stone suddenly came into the light. Many springs throughout the Mojave and its surrounding ranges were associated with stories, with spiritual significance, with responsibilities of care and stewardship that were passed down through generations. The obligation to know where water was and to maintain right relationships with those water places was not separate from spiritual life. It was continuous with it. Caves and rock shelters, some of which penetrated the ground to depths that felt genuinely underground, were also places of significance across many desert cultures of the Southwest. The transition from the open desert into the cool darkness of a cave or deep rock shelter was a transition between worlds in a literal physical sense, and in many traditional cosmologies, a meaningful threshold in other senses as well. Rock art appears at cave and shelter sites throughout the region, sometimes in positions or with characteristics that suggest these were not simply convenient walls, but specifically chosen locations. The cosmologies of many desert peoples included understandings of the earth itself as layered, with the surface world connected to worlds above and worlds below through specific places and through specific practices. Water emerging from underground, the coolness of a cave, the darkness of a deep fissure, these were not frightening anomalies but recognizable features of a landscape understood through a framework that encompassed both surface and underground as parts of a single, coherent world. The landscape memory encoded in place names deserves particular attention here. Indigenous place names throughout the Mojave and surrounding region often describe features of the landscape with remarkable precision, features that include springs, caves, rock formations, and geological characteristics that might not be obvious to an outside observer, but that were central to the practical and cultural geography of the people who assign those names. This encoded geographical knowledge represents a form of mapping far older and in some ways more complete than anything produced by later surveys. A mapping of the Mojave that took thousands of years to accumulate, and that was carried in language and story rather than on paper. One of the most significant documented examples of indigenous knowledge informing modern understanding of the Mojave's underground features involves the relationship between traditional accounts of underground water and the locations of springs and seeps documented by later hydrological surveys. In a number of cases, springs known to indigenous communities and referenced in oral traditions have turned out, upon later scientific investigation, to be connected to underground water systems of considerable extent and complexity. The knowledge of where water moved underground was not abstract or mythological. It was practical, precise, and accurate in ways that modern science has repeatedly confirmed. John Wesley Powell, whose 1869 expedition through the Grand Canyon is one of the most celebrated journeys of Western American exploration, wrote extensively about his interactions with Southern Paiute guides during later surveys of the region. He noted that his Paiute companions possessed detailed and reliable knowledge of water sources, travel routes, and landscape features across an enormous range of territory, knowledge that he acknowledged made their guidance indispensable. Powell was more attentive to indigenous expertise than many of his contemporaries, though even his accounts reflect the assumptions and limitations of his era. Different indigenous nations preserved different traditions and relationships with the desert. This is a fact worth sitting with quietly for a moment. The Mojave Desert was not a single thing to all the people who inhabited it. It was many different deserts, understood through many different frameworks, remembered in many different languages, crossed by many different routes, and related to through many different forms of knowledge and practice. The underground world that we are exploring in this documentary was part of all of those understandings, in ways and in depths that belong to those communities and to the ongoing work of the scholars, both indigenous and non-indigenous, who work with those communities to document and preserve that knowledge. What that knowledge makes clear, above all else, is that when the first Anglo-American prospectors began arriving in the Mojave in the mid-19th century, they were not entering a wilderness. They were entering a landscape that had been inhabited, known, named, mapped in the most precise possible sense, and cared for across thousands of years. They carried their own frameworks for understanding desert landscapes, frameworks built around resource extraction and economic opportunity, and those frameworks shaped what they saw, what they looked for, and what they found. But the underground world that they began to explore with picks and black powder and flickering lanterns, following veins of ore deeper and deeper into the rock, was a world that had already been observed, and in some places entered by people who understood it through a very different and much older lens. The first Anglo-American expeditions into the Mojave Desert were not looking for beauty or geological curiosity or a deeper understanding of the underground world. They were looking for a route, a way through. The Mojave proved itself to those earliest travelers to be exactly what the desert has always been to those who approach it without sufficient preparation or knowledge. It was punishing, it was disorienting, it was relentless in its demands and stingy with its concessions. Jedediah Smith, the mountain man and explorer, who in 1826 became one of the first Anglo-Americans to cross the Mojave Desert, described the experience with a directness that leaves no room for romanticism. His party suffered from extreme thirst, struggled to find reliable water, and lost animals to the heat and the distances between springs. Smith crossed the desert twice, once westward and once eastward, and both crossings left him with a clear-eyed respect for the landscape that he expressed in the practical language of someone who understood survival. The trails that eventually became established across the Mojave, routes like the Old Spanish Trail and later the Salt Lake Road, followed water sources with the careful logic of necessity. They were not direct routes. They bent and curved according to the locations of springs and seeps, many of which had been known to indigenous peoples for generations and were learned by Anglo travelers partly through indigenous guidance and partly through hard-won experience. The trails that appear straight on old maps are, when you look more closely, a series of connected arcs between water points, each segment representing the maximum reasonable distance a person or animal could travel without water under desert conditions. It was along and near these travel corridors that the first mineral discoveries were made. The geology of the Mojave, that complex system of basin and range faulting, ancient volcanic activity, and deep crustal fracturing, created conditions favorable to the concentration of valuable minerals in specific locations. Gold, silver, copper, lead, tungsten, and other metals were deposited along fault zones and in certain rock formations through hydrothermal processes. The movement of hot, mineral-laden water through fractures in the Earth's crust during periods of volcanic and tectonic activity. When those waters cooled and precipitated their dissolved minerals, they left behind veins of ore locked in the surrounding rock, waiting for whoever eventually came looking. The California Gold Rush of 1848 and 1849 sent prospectors fanning out across the western landscape in search of minerals, and the Mojave Desert lay directly in the path of that expansion. By the 1860s, mining camps had begun to appear at scattered locations across the desert, each one following a discovery of ore that seemed promising enough to justify the extraordinary logistical challenges of working in such a remote and inhospitable environment. The Calico Mountains, rising above the Mojave Valley near present-day Barstow, became the site of a significant silver mining boom beginning in 1881. Silver had been discovered in the steep-sided canyons of the Calico Range, and within a few years, a town of several thousand people had materialized from the desert floor, complete with saloons, a newspaper, a school, and the entire social infrastructure that follows concentrated human economic activity. The mines at Calico eventually produced an estimated $86 million in silver at historical prices, an amount that represents only a fraction of the geological wealth contained in the surrounding rock. The Randsburg mining district, located in the Rand Mountains near the southern edge of the Mojave, produced gold beginning in 1895, when a discovery triggered a rush that drew thousands of prospectors to the area. Randsburg produced gold through much of the early 20th century, and its mines revealed something about the underground landscape of the Mojave that would not have been apparent from the surface. The ore-bearing formations extended downward to considerable depths, following the fault and fracture systems created by basin and range tectonics, descending into the earth along paths that had been prepared by geological forces active long before the gold was deposited. Mining is, in its most fundamental sense, a form of underground exploration. The prospectors and mining engineers who worked the Mojave's ore deposits were the first people to penetrate the underground landscape of this desert in a systematic and sustained way. They sank shafts straight down through desert rock, following veins of ore wherever they led. They drove horizontal tunnels, called adits, into hillsides to access ore bodies at depth. They created underground workings of considerable extent, networks of passages and chambers that in some cases extended for hundreds of feet, both vertically and horizontally. In doing so, they also encountered, and sometimes documented, the natural underground features that existed alongside and beneath their excavations. Miners working in certain areas of the Mojave broke through into natural cave chambers while following ore veins. They encountered underground springs and seeps that filled their workings with water. They found sections of their tunnels passing through lava tubes and natural passages that pre-existed any human excavation by thousands or millions of years. The borax industry added another dimension to the Mojave's underground story. Borax, the mineral sodium tetraborate, was found in vast deposits in the dry lake beds of the Mojave, particularly in the Death Valley region and surrounding areas. The process by which borax was deposited in these lake beds is itself an underground story, involving the evaporation of ancient lakes and the concentration of mineral-laden groundwater over geological time. Coleman's borax operation in the late 19th century, made famous by the 20-mule teams that hauled wagite ore wagons across the desert to the nearest railroad, represented one of the largest industrial operations the Mojave had yet seen. And it depended entirely on an understanding of the geological processes that had concentrated mineral wealth in the desert's dry basins. The railroad followed, or in some cases preceded and encouraged, the mining activity. The Atlantic and Pacific Railroad, later reorganized as the Atchison, Topeka, and Santa Fe, crossed the southern Mojave in the early 1880s, connecting the mining districts to markets and supplies. The railroad made large-scale mining economically viable in locations where the cost of hauling ore by wagon across hundreds of miles of desert had made even rich deposits barely profitable. With the railroad came easier access to the desert, and with easier access came more prospectors, more exploration, and more discoveries, but also more abandoned camps, more failed shafts, more lost investments. The history of Mojave mining is not simply a story of wealth extracted from the earth. It is equally a story of hardship, failure, and the humbling power of a landscape that offered its mineral riches only at considerable cost. For every successful mine that produced reliably for years or decades, there were many more that yielded only modest ore before the vein pinched out. Or the water flooding the workings became too expensive to pump, or the price of the ore collapsed on distant markets before the mining company had recovered its investment. The abandoned shafts and adits that dot the Mojave landscape today are the physical record of that complex history. They are also, in many cases, doorways into an underground world that was partly natural and partly human-made. A hybrid landscape where the geological structures that miners exploited for ore exist, alongside natural cave systems that their tunnels occasionally intersected. Most of those shafts are sealed now, or partially collapsed, or gated by conservation agencies to prevent dangerous access, while still allowing the passage of bats and other cave-dwelling animals that have made them their homes. They stand in the desert as quiet markers of a period when the underground world of the Mojave was first penetrated in a large-scale, systematic way. The prospectors who sank those shafts understood themselves to be looking for ore, for silver and gold and copper and borax. They were not, for the most part, thinking about geological history or cave systems or the underground hydrology of the desert they were digging into. But in following the veins of ore downward into the earth, they created a vast network of underground passages that, combined with the natural cave systems already present, gives the Mojave one of the most complex and least understood underground landscapes in North America. They revealed, without fully realizing it, only the tiniest fraction of what lies below. The surface of the desert told one story. The underground, glimpsed only partially through the narrow windows of mine shafts and natural cave entrances, told another. And between those two stories, in the vast unmapped spaces between documented features, the real underground Mojave waited and continues to wait, patient as geology itself. There is a moment that experienced cave explorers describe, a moment that comes not with drama, but with a kind of quiet certainty, when you realize that the passage you are moving through extends further than your light can reach. You press forward, carefully, one hand on the wall, your headlamp cutting a narrow cone of illumination through air that has not moved in years, perhaps centuries. The ceiling rises and falls. The floor shifts from smooth flowstone to loose breakdown, chunks of fallen rock that shift under your weight and must be tested before each step. The temperature is constant, cool and still, somewhere between 50 and 60 degrees regardless of what the desert above is doing. And then the passage opens, unexpectedly, into a chamber larger than your light can fully illuminate, and you understand in a sudden, physical way that this place is bigger than you thought, much bigger, and that you have only just arrived at its edge. This is the experience of exploring the underground Mojave, not the entire underground Mojave, of course. Most of it has never been entered by any person. What has been explored, what has been mapped and documented and surveyed by the geologists and speleologists and volunteer cave explorers who have worked in this region over the past several decades, represents a small and carefully documented portion of a much larger and mostly unknown underground world. To understand why so much remains unmapped, it helps to think about the scale of the Mojave Desert itself, 47,000 square miles, an area larger than the entire state of Pennsylvania. Across that vast extent, the geological conditions we have described, the lava tubes, the karst features in limestone formations, the fault-controlled passages, the abandoned mine networks, the collapsed volcanic chambers, exist at a density that has never been fully inventoried. There is simply no comprehensive catalogue of underground features in the Mojave Desert. Such a catalogue does not exist because the surveys required to produce it have not been completed, and the resources and time required to complete them would be extraordinary. What does exist is a patchwork of documented features, individual cave surveys, mapped lava tube sections, recorded mine workings, and documented karst features, scattered across the desert in patterns that suggest something much larger lying between the known points. Within Mojave National Preserve alone, which covers approximately 1.6 million acres in the eastern Mojave, surveys have documented dozens of cave features. Some of these are small and relatively simple. Others are considerably more complex. The preserve's volcanic fields, particularly the Sima volcanic field, with its well-preserved cinder cones and lava flows, contain lava tubes that have been partially mapped, but whose full extent remains uncertain. The limestone formations in the Providence and New York mountain ranges contain karst features that have been documented in part, but not comprehensively surveyed. Outside the preserve, across the broader Mojave Desert, the situation is similar. Individual mining districts contain extensive underground workings that are recorded in historical mining records of varying completeness. Natural cave features are documented at some locations and entirely unknown at others. The relationship between natural cave systems and mine workings, the degree to which the two overlap, intersect, or exist in parallel without connection, has been worked out in some locations and is entirely unknown in others. The reasons for this incomplete knowledge are practical and unglamorous. Cave exploration in the Mojave is genuinely dangerous. The desert environment creates specific hazards that are different from those encountered in more humid cave environments. Lava tubes in arid environments can be structurally unstable in ways that are difficult to predict, with ceilings that appear solid but may be weakened by millennia of thermal cycling and chemical weathering. Abandoned mine shafts present hazards that include not only structural instability, but also the accumulation of oxygen-depleted air, carbon dioxide, and toxic gases from the oxidation of sulfide minerals in the surrounding rock. The extreme temperatures of the Mojave surface make access itself a challenge. In summer, surface temperatures in excess of 115 degrees Fahrenheit can make even a short approach hike to a cave entrance genuinely life-threatening. In winter, flash flooding can move through desert cave systems with terrifying speed, filling passages that are perfectly dry and safe 1 hour and impassable the next. The logistical requirements for safe cave exploration in this environment, water, communications equipment, first aid capability, multiple experienced personnel, are more demanding than those for cave exploration in more accessible environments. Conservation restrictions add another layer of complexity. Many cave features within national park and preserve lands are protected, rightly, from uncontrolled access. White nose syndrome, the fungal disease that has devastated bat populations across North America, has made the management of cave access an urgent conservation priority, and many caves that might otherwise be surveyed are restricted to protect their bat populations from additional disturbance. The National Park Service and Bureau of Land Management both manage cave resources within their jurisdictions under legal frameworks that require documentation, permits, and careful management of any exploration activities. The scale of the underground problem in the Mojave was brought into clearer focus by surveys conducted in and around Mojave National Preserve beginning in the 1990s, when the preserve was established and systematic resource inventories began. Those surveys confirmed what experienced local cavers had long suspected: that the underground of the eastern Mojave contained substantially more cave passage than had been formally documented, and that the relationship between the natural cave systems and the extensive mine workings of the region was complex and in many places unclear. One of the consistent findings of cave surveys in volcanic regions of the Mojave is that documented lava tubes frequently connect to additional passage beyond their mapped sections. A tube that appears to end at a breakdown pile, a heap of collapsed ceiling material, may continue beyond the collapse in a passage that simply requires excavation of loose material to access. Whether that excavation is appropriate, given conservation concerns and resource protection requirements, is a management question that does not always have a simple answer. The fault-controlled passages that exist along major fracture zones in the desert are another category of underground feature whose extent is genuinely unknown. Fault zones can create linear corridors of broken and displaced rock extending for many miles, and within those corridors, natural passages can form through the collapse and dissolution of fault-weakened rock. Some of these passages are accessible, others are sealed by subsequent geological events. Others may be accessible only through openings that are too small or too dangerous to enter safely. The abandoned mine network of the Mojave represents a particularly complex underground landscape. Historical mining records, where they exist and have been preserved, provide some information about the extent of underground workings in specific mining districts. But those records are incomplete, inconsistent, and in many cases simply lost. Mines were opened and abandoned, reopened and extended, sealed and collapsed, sometimes over periods spanning several decades and multiple owners. The underground workings that resulted are not always accurately described in any surviving documentation. More significantly, some of the most extensive mine workings in the Mojave were developed in ore bodies that followed natural geological structures, including fault zones and cave systems, meaning that the boundary between human excavation and natural passage in some of these workings is genuinely unclear without direct investigation. A miner following an ore vein into a natural cave chamber and continuing the vein on the far side has created a hybrid underground space that is neither purely natural nor purely artificial. How much of the Mojave's underground remains unmapped simply because the desert refuses easy exploration? The honest answer is that we do not know, and that honest uncertainty is itself one of the most interesting things about this landscape. We are not speaking about a region that has been thoroughly investigated and found to contain a modest and well-understood underground world. We are speaking about a region where the combination of geological complexity, extreme access conditions, conservation requirements, and sheer scale has meant that the underground surveys conducted to date have barely scratched the surface of what is actually there. Every documented cave in the Mojave points toward potentially many more undocumented ones. Every mapped section of lava tube implies passage beyond its end. Every sealed mine shaft is a door that may or may not open into something natural, something old, something that has been sitting in cool darkness since long before any human being arrived in this desert. The underground Mojave is not a mystery because anyone has concealed it or restricted access to it. It is a mystery because it is genuinely large, genuinely complex, genuinely dangerous to explore, and genuinely patient. It does not need to reveal itself on any human timeline. It has been building itself for millions of years, and it will continue building itself long after the last map has been drawn and the last shaft has been sealed. That patience, that indifference to human curiosity is itself a kind of grandeur. Every landscape that has tested human endurance long enough eventually acquires its ghost stories. The Mojave is no exception. The folklore of the desert, accumulated across the decades of the mining era and amplified through the campfire storytelling tradition of prospectors, freighters, and desert travelers, contains a rich collection of legends, mysteries, and unanswered questions. These stories are not historical evidence. They are not geological data. They are something different, and in their own way, something worth listening to, not because they are true in a literal sense, but because they tell us something about how human beings respond to a landscape this vast, this severe, and this genuinely unknown. The Lost Mine story is perhaps the most persistent of all Mojave Desert folklore traditions. Virtually every mining region in the American West has its version, a mine of legendary richness, discovered by an individual or small group of prospectors who, for various reasons, death, illness, confusion, the obliterating sameness of desert terrain, were unable to return to it or communicate its location clearly to anyone else. The ore samples they brought back were rich beyond normal expectations. The mine itself has never been relocated. The Mojave has several of these legends, each with its own particular flavor and history of telling. The Lost Arch Mine, the Lost Pegleg Mine, and various unnamed lost Spanish mine traditions circulate through the folklore of the desert in versions that have shifted and accumulated detail across generations of retelling. These stories share certain structural elements, a discovery under unusual circumstances, or of exceptional richness. A return journey made difficult by desert conditions, and then a failure to relocate the site that spawns decades of searching. It is important to be direct about what these stories are and are not. They are folklore, regional storytelling traditions that serve real social and cultural functions. They create community among the people who tell them, provide a framework for the romantic imagination of desert exploration, and express something genuine about the experience of moving through a landscape this large and this full of actual geological variety. The Mojave does contain mineral deposits, some of which were never fully documented or developed during the mining era. Ore-bearing formations do exist in areas that were not thoroughly prospected. These are geological facts. But the specific lost mine legends, with their tales of extraordinary richness and their frustrating near-recoveries, belong to folklore rather than history. The distinction matters. Folklore tells us about human experience and human imagination. History tells us what happened. These are not the same thing, though they can be related. The phantom miner tradition is another strand of Mojave folklore worth understanding on its own terms. The desert's extreme conditions, its isolation, its disorienting sameness across vast stretches of terrain created real dangers for the prospectors and travelers who moved across it in the 19th and early 20th centuries. People did die in the Mojave of thirst and heat and exposure and accident. The desert was genuinely unforgiving of errors in judgment, insufficient water, or simple bad luck. Out of this reality grew a body of stories about figures seen in the desert and then not found, voices heard in canyons where no one was visible, the sounds of tools working on rock in the quiet desert night with no visible source. Desert acoustics, the way sound travels across flat valley floors and reflects from canyon walls, can produce genuinely puzzling auditory experiences. Sound that originates at a considerable distance can arrive at unexpected intensity and from unexpected directions in certain desert conditions. The desert also produces optical illusions, mirages, and the distortions of heat shimmer that can create the appearance of structures, vehicles, or figures where none exist. These physical realities of the desert environment provided fertile ground for storytelling. The phantom miners, the lost souls still searching for their claims, the lights seen moving in the hills above old mining camps, are expressions of that ground. They also express something more universal: the human discomfort with not knowing, the desire to populate the unknown spaces of a landscape with some kind of presence, even an unsettling one, rather than leaving them simply empty and indifferent. The Spanish mine legends deserve particular mention because they have a slightly different character from the purely folkloric lost mine stories. Historical records do document the presence of Spanish colonial expeditions in portions of the Greater Southwest, and some small-scale prospecting and mining activity did occur in the broader region during the Spanish colonial period. The Mojave Desert proper, however, was not a major center of Spanish colonial mining activity. The legends of vast Spanish mines hidden in the desert, with their romantic overtones of conquistadores and buried treasure and secret maps, draw more on the general mythology of the Southwest than on specific documented history. There is something worth noting about the geography of these legends. Many of the most persistent lost mine stories in the Mojave are set in terrain that is genuinely difficult to access in deep canyons on the far sides of dry mountain ranges. In areas where the natural landmarks that a prospector might use to relocate a site are genuinely confusing and unreliable. This is not an accident of storytelling. It reflects something true about the desert, which is that its terrain, particularly in the more dissected mountain ranges, can be genuinely disorienting in ways that make accurate navigation without modern instruments difficult. A prospector who found an outcropping of rich ore in a side canyon of the Providence Mountains navigated to it across featureless desert terrain by dead reckoning and the position of the sun, and then tried to relocate it after a period of illness or absence, might genuinely have struggled to find it again. The landscape has a way of looking completely different depending on the direction from which you approach it, the time of day, the season, and the particular trick of light that the desert exercises over the human eye. This practical reality of desert navigation provides a plausible foundation on which the more elaborated folklore structures of the lost mine tradition were built. The cave acoustics that form part of this folkloric landscape are real and genuinely strange. Large underground chambers can produce sound reflections that distort the apparent location, distance, and nature of sound sources. The movement of air through underground passages creates sounds that range from a barely perceptible breath to a low moan to something that, in certain passages and certain wind conditions, sounds remarkably like a human voice. The dripping of water in cave chambers produces rhythmic sounds that can carry surprisingly far through the acoustics of enclosed stone spaces. Miners working deep in the rock would have encountered these sounds regularly in the resonant chambers of their own excavations, and where those excavations intersected natural cave features in the stranger acoustics of spaces shaped by geological rather than human design. It is not difficult to understand how the sounds of a cave, heard in the flickering light of a lantern at the end of a long shift underground, found their way into the storytelling tradition of the mining camps above. These stories belong to the Mojave in a different but genuine way than its geology or its archaeology. They are part of the human response to a landscape that has always exceeded easy understanding. They acknowledge, in the language of imagination rather than science, that this desert contains more than is visible on its surface, more than has been mapped or measured or explained. That acknowledgement, even in its folkloric form, points towards something true. The campfire stories of the Mojave mining era have faded now, passed down in fragments through local history collections, newspaper archives, and the memories of families with roots in the desert communities of the late 19th and early 20th centuries. But the landscape that generated them is unchanged. The canyons are still deep. The terrain is still disorienting. The desert night is still full of sounds that the wind makes as it moves through stone. And the underground world that those stories orbited, never quite naming it, but always sensing it, that world is still there. Quiet and cool and immeasurably patient. In a cave beneath the Mojave Desert where no sunlight has ever reached, and no surface temperature fluctuation ever penetrates, a small brown bat hangs from the ceiling in a cluster of several hundred of its kind, their wings folded tight against their bodies. Their heart rate slowed to a fraction of their active pace. Outside, on the desert above, the temperature is 108 degrees. Inside the cave, it is 54. The bats do not know this. They do not need to know it. The cave is doing what caves do in desert environments, providing a thermal refuge so stable and so consistent that it functions as a kind of biological sanctuary in the middle of one of the most thermally extreme landscapes on the continent. The cave ecology of the Mojave Desert is a subject that has received increasing scientific attention over the past several decades, and what that attention has revealed is genuinely remarkable. Caves in desert environments are not simply empty voids, geological curiosities without biological significance. They are habitats, often irreplaceable ones, hosting communities of organisms that have adapted over long periods to conditions that exist nowhere on the surface. The bats are the most visible and in many ways the most ecologically important members of these underground communities. Several bat species use caves and abandoned mine shafts in the Mojave Desert as roosting sites, both for summer maternity colonies, where females gather to give birth and raise their young, and for winter hibernation. The Townsend's big-eared bat, a species with extraordinary acoustic sensitivity and distinctively large ears that fold along the sides of its head when not in use, is one of the cave-dependent species found in the Mojave region. The western long-eared myotis, the pallid bat, and several species of myotis bats also use cave and mine features throughout the desert. The relationship between these bat populations and the cave systems of the Mojave is not incidental. It is deep and long established. Bats have been roosting in desert caves for thousands of years, accumulating deposits of guano, their droppings, that build up in cave chambers over time into layers that contain a biological and chemical record of the bat populations and their food sources across centuries. Guano deposits in desert caves can be several feet deep in locations that have been used continuously for extended periods, and the analysis of those deposits has yielded information about the history of insect populations in the region, about past climate conditions, and about the long-term ecology of the cave systems themselves. The threat posed by white nose syndrome to these populations is not abstract. This fungal disease, caused by the pathogen Pseudogymnoscus destructans, has killed millions of bats across North America since it was first identified in New York in 2006. It has spread steadily westward, and its arrival in the Mojave region and surrounding areas has been a source of serious concern for conservation biologists working with cave-dwelling bat species. The management implications for cave access in the Mojave are significant because the fungal spores that cause white nose syndrome can be carried on clothing, equipment, and footwear between cave sites, meaning that uncontrolled human access to bat caves poses a real risk to populations that may already be under pressure. Beyond the bats, the cave communities of the Mojave support organisms that are less familiar but no less biologically interesting. Cave invertebrates, the insects, spiders, crustaceans, and other small animals that have adapted to underground life, are present in Mojave caves in forms that range from the merely unusual to the genuinely remarkable. Some cave invertebrates in desert environments are what biologists call troglophiles, species that can live either in caves or on the surface and move between the two. Others are troglobites, species that are obligate cave dwellers, unable to survive on the surface and found nowhere outside of cave environments. Cave-adapted versions of familiar surface species often show the characteristic modifications that natural selection produces in organisms living in perpetual darkness with limited food resources. Eyes may be reduced or absent, since the energetic cost of developing and maintaining visual systems is not justified in an environment with no light. Pigmentation is often reduced or absent for similar reasons. Sensory organs used to detect vibration, chemical signals, and air movement are often enhanced compared to surface relatives, compensating for the absence of vision with heightened sensitivity to other environmental cues. The caves and mine shafts of the Mojave also harbor microbial communities of extraordinary diversity. The science of cave microbiology has expanded rapidly over the past 2 decades, driven by advances in genetic sequencing technology that allow researchers to identify and characterize microbial organisms without needing to culture them in a laboratory. What those advances have revealed in cave environments around the world, including desert caves, is that the microbial diversity of cave ecosystems is remarkable, often containing species that are found nowhere else, and that have metabolic capabilities adapted to the specific chemical and energetic conditions of their underground habitat. Some cave microorganisms in arid environments obtain their energy not from organic material deposited from the surface, but from chemical reactions involving minerals in the cave walls. This process, called chemolithotrophy, allows microbial communities to exist in cave environments that receive essentially no input of organic material from the surface world above. They are, in a very real sense, entirely independent ecosystems living on the chemistry of the rock itself. The mineral formations that decorate Mojave caves represent another dimension of the underground biological story, because the relationship between microbial activity and speleothem formation, the growth of stalactites, stalagmites, and other cave deposits, is an active area of scientific research. Microorganisms can influence the precipitation of minerals from cave waters, and the distinctive mineral formations found in desert caves often reflect the specific chemical conditions of those environments. Desert cave speleothems, the mineral formations deposited by dripping or flowing water, are different in character from those found in wetter cave environments. Where a cave in a humid region might support actively growing stalactites dripping year-round, a desert cave may have speleothems that grew during wetter climatic periods and are now essentially static, their growth slowed or halted by the reduction in available water. These formations are, in a sense, fossilized records of past wet periods, physical evidence in the rock of the wetter climates that characterized the Mojave during the Pleistocene and early Holocene. The humidity within desert caves, even in an environment as dry as the Mojave, tends to be significantly higher than the humidity of the desert surface. The rock surrounding the cave moderates temperature and reduces the movement of dry air, allowing moisture to accumulate in concentrations that support biological communities and mineral processes that would be impossible on the baked surface above. Small insects, microbes, and fungi exploit this humidity, creating biological communities sustained by an energy source as modest as organic material blown in on the wind or carried in by bats. The underground humidity also supports the slow movement of water through cave walls, a seepage so gradual that individual drops may take years to work their way through the overlying rock and reach a cave ceiling. But those drops carry dissolved minerals that, precipitating at the point where the drop falls from ceiling or wall, contribute grain by grain to the mineral formations below. In the Mojave, this process is slow beyond ordinary human perception. A stalactite that might grow measurably in a humid cave environment may grow only a fraction of a millimeter per century in the drier conditions of a desert cave. But given sufficient time, even this rate of growth produces formations of remarkable size and beauty. There is something deeply settling about the ecology of these underground spaces. Above, the desert operates at extremes that make survival a constant negotiation. Temperature, water availability, solar radiation, the thermal violence of the Mojave's daily temperature cycle, all of these create an environment that demands constant adaptation and constant expenditure of energy just to remain alive. Below, in the cool and constant darkness of the cave, a different logic operates. Energy is scarce, but conditions are stable. The organisms that have found their way into these underground spaces and adapted to them over generations live in a world where the temperature never changes, where the wind never blows, where the brutal noon sun is as remote and irrelevant as a story told about somewhere else entirely. They live, in other words, in the Mojave's most hospitable environment, an environment created not by any moderation of the desert's extremes, but by escape from them entirely, by going deep enough into the rock that the surface world becomes irrelevant. That is an adaptation worth appreciating for a moment in the quiet way that this documentary has been moving through the Mojave. The desert above is fierce and demanding. The desert below has found a way to be still. On a cool November morning in the eastern Mojave, a small team of researchers stands at the edge of a lava field, preparing equipment before the sun has fully cleared the Providence Mountains to the east. Their gear is not the gear of the 19th century prospectors who worked this same ground 150 years ago. There are no picks, no lanterns, no leather canteens. Instead, there are laptops in padded cases, a drone folded into a backpack, handheld GPS units, and a ground-penetrating radar antenna mounted on a wheeled frame that looks, at first glance, a little like an unusually purposeful lawnmower. The team speaks quietly, checking instruments, reviewing the day's survey plan on a tablet screen that displays a topographic map covered in colored polygons marking areas of geological interest. They are here to look for caves without going into them. Or more precisely, they are here to find out where caves might be before anyone commits to the significant logistical challenge and safety planning required to enter and document them directly. This is modern cave science in the Mojave Desert. It is patient, methodical, and often unglamorous. And it is slowly building a picture of the underground that would have been impossible to imagine in the era of the prospectors. The technologies available to researchers studying underground features in the Mojave today represent a transformation in what is knowable about the subsurface landscape without direct entry. Each technology has its strengths and limitations, and each contributes a different kind of information to a picture that is assembled piece by careful piece over years of sustained effort. LiDAR, which stands for light detection and ranging, is one of the most powerful tools available for detecting surface expressions of underground features. The technology works by emitting rapid pulses of laser light from an aircraft or drone and measuring the time it takes for those pulses to return after bouncing off the ground surface. By collecting millions of these measurements across a survey area, researchers can build a digital elevation model of the terrain with a level of precision and detail that was previously impossible. What makes LiDAR particularly valuable in cave research is its ability to reveal subtle surface features that are invisible to ordinary aerial photography or ground-level observation. A lava tube collapse, a place where the ceiling of a buried tube has fallen inward, creating a linear depression or a series of pit-like features at the surface, can be entirely invisible to the eye when walking across the desert. The vegetation cover, the irregular surface texture of the lava field, and the play of light and shadow can conceal these features completely. But a LiDAR-derived elevation model, stripped of vegetation and analyzed at high resolution, can reveal the linear depressions and subtle topographic signatures of buried tubes with remarkable clarity. Researchers working in volcanic regions similar to the Mojave have used LiDAR to identify dozens of previously undocumented lava tube systems by mapping surface depressions associated with tube collapses. In the Mojave specifically, LiDAR surveys of the volcanic fields in and around Mojave National Preserve have contributed to an improved understanding of where buried tube systems are likely to exist, even where no accessible entrance has yet been identified. Ground-penetrating radar, or GPR, operates on a different principle. It emits pulses of radar energy into the ground and measures the reflections that come back from subsurface features. Different materials, rock, air, water, sediment, reflect radar energy differently, allowing the instrument to detect voids, changes in rock type, and other subsurface variations. In the right geological conditions, GPR can detect cave voids beneath the surface to depths of several meters, providing information about the location, shape, and approximate size of underground features without requiring any excavation or entry. The limitations of GPR in the Mojave context are real. The technique works best in relatively homogeneous rock, and the complex, heterogeneous geology of desert volcanic fields and fault zones can produce confusing reflections that are difficult to interpret. The depth of penetration is also limited by the electrical properties of the rock, which vary considerably across the Mojave landscape. Nevertheless, GPR has been used effectively in certain locations to confirm the presence and approximate dimensions of underground voids detected by other methods, adding a layer of verification to surveys that might otherwise rely solely on surface observations. Drone technology has transformed the accessibility of remote cave entrances and the quality of documentation possible in the field. Small unmanned aerial systems equipped with high-resolution cameras and GPS can survey terrain that would require days of difficult hiking to access on foot, identifying potential cave entrances, mapping collapse features, and providing aerial context for ground-level observations. Some research teams have begun using drones equipped with LiDAR sensors, allowing high-resolution subsurface mapping to be conducted in areas too remote or too rugged for conventional aircraft operations. More recently, researchers have begun exploring the use of thermal imaging technology in cave detection. Caves in desert environments often have temperatures significantly different from the surrounding rock, and in certain atmospheric conditions, particularly at dawn and dusk, when surface temperatures are changing rapidly, the temperature difference between a cave entrance and the surrounding terrain can be detected by thermal sensors. Aircraft or drone-mounted thermal cameras can potentially identify cave entrances as thermal anomalies in the landscape, flagging locations for ground investigation that might otherwise be overlooked. Hydrogeological research contributes a different but equally important dimension to the mapping effort. Understanding where underground water moves through the Mojave, how deep the aquifer systems lie, and where groundwater discharges at the surface as springs and seeps, provides indirect evidence about the structure of the underground rock. Water follows pathways created by fractures, fault zones, and soluble rock formations, and mapping those pathways through hydrogeological analysis can reveal the architecture of the underground without direct entry into it. Isotopic analysis of water samples from springs, wells, and surface drainages has been used extensively in the Mojave region to characterize the age and origin of groundwater, the pathways it has followed through the underground rock, and the connections between different parts of the hydrological system. This research, conducted by university research groups and by agencies including the United States Geological Survey, has built a progressively more detailed picture of the Mojave's underground hydrology over the past several decades. The speleological community, the network of trained volunteer cave explorers who work alongside professional scientists in documenting cave systems, contributes an irreplaceable ground-level dimension to all of this remote sensing and analytical work. The National Speleological Society and its affiliated grottos, local caving clubs organized across the country, have members with extensive experience in the Mojave and surrounding desert regions. These volunteers undergo technical training in cave exploration safety, survey techniques, and conservation practices, and they contribute thousands of hours of fieldwork to the documentation of cave systems that professional researchers, with limited budgets and competing demands on their time, could not survey alone. Cave survey methodology, the process by which the dimensions and shape of a cave are measured and recorded as a map, is exacting work. Survey teams move through a cave in a careful, systematic way, measuring distances with a tape or laser rangefinder, recording compass bearings and inclination angles at each survey station, and noting the width, height, and character of the passage at each point. The resulting data is entered into specialized software that constructs a three-dimensional model of the cave from the survey measurements, producing a map that represents the cave's geometry with a level of precision appropriate to its scientific and conservation management value. In the Mojave, cave surveys have documented features ranging from simple lava tube sections, a few hundred feet long, to more complex underground systems with multiple passages, chambers, and vertical elements. Each survey, however modest in scope, adds to the permanent scientific record and contributes to an understanding of the region's underground that is larger than any individual expedition. Mine safety research has also contributed to the understanding of the Mojave's underground, if in a somewhat different register. The Bureau of Land Management and the Mine Safety and Health Administration have conducted assessments of abandoned mine features across the Mojave Desert, both to address the public safety hazard posed by open shafts and unstable workings, and to evaluate the conservation value of mine features that provide habitat for bats and other cave-dwelling species. These assessments have produced documentation of mine workings that, in some cases, represents the most complete existing record of underground features in certain parts of the desert. Conservation management of cave resources in the Mojave operates within a framework established by the Federal Cave Resources Protection Act of 1988, which requires federal land management agencies to identify, study, and protect significant cave resources on public lands. The implementation of this framework in the Mojave has driven systematic cave inventory work within Mojave National Preserve and other federally managed lands in the region, contributing substantially to the documented understanding of the underground. The picture that emerges from all of these research streams, from LIDAR surveys and ground-penetrating radar from hydrogeological analysis and speleological surveys from mine assessments and conservation inventories, is one of a genuinely vast and complex underground landscape in which every expedition, every survey, every careful measurement adds another small piece to an immense and still mostly incomplete picture. The researchers who work in this landscape understand this with a clarity that comes from direct experience. They know in a way that is difficult to communicate without having stood at the end of a mapped passage, looking into darkness that extends beyond any light they carry, that what has been documented is a beginning rather than a conclusion. The underground Mojave is not a solved problem. It is a research frontier in the truest sense of that phrase, a place where the boundary between what is known and what is unknown is actively being pushed forward, year by year, survey by survey, one careful measurement at a time, and the desert is not making it easy. But then it never has. There is a quality to mystery that persists in genuine form only when the thing being wondered about is genuinely large. Small mysteries resolve themselves eventually. A question with a bounded number of possible answers yields, in time, to sufficient investigation. But some landscapes, some geological systems, some combinations of scale and complexity and inaccessibility present mysteries that are not bounded in that way. Mysteries that do not diminish as knowledge grows, but that simply reveal new dimensions of themselves as each previous dimension is mapped and understood. The underground Mojave is that kind of mystery. Every lava tube that has been surveyed and mapped exists within a volcanic field that contains potentially dozens more unexamined tubes. Every karst cave documented in the limestone ranges of the eastern Mojave suggests the possibility of additional dissolution features in the same rock formations, in adjacent canyons, on the far sides of ridges that have not yet been walked by anyone with survey equipment. Every mine shaft that has been assessed and recorded points toward the complex underground geology that the miners were following, geology that may express itself as additional natural features in surrounding areas that were never mined. The unmapped lava tubes of the Mojave represent perhaps the most straightforward category of underground mystery, in the sense that the geological process that creates them is well understood, and the volcanic fields in which they occur are clearly defined. What is not known is how many tubes exist within those fields, how extensive their total passage length is, and what specific features and biological communities they contain. The Cima volcanic field, as we noted earlier, is one of the youngest and best preserved volcanic landscapes in the contiguous United States. Its lava flows are geologically recent enough that surface erosion has not yet significantly degraded the original topography, meaning that the tube systems that formed within those flows may be relatively intact, their ceilings still structurally sound, their passages still open rather than collapsed. What surveys have been conducted in the Cima field have revealed tube features, but the field covers an enormous area, and systematic survey of its full underground potential has not been completed. Other volcanic areas within and adjacent to the Mojave, including the Pisgah crater area near Barstow and the Amboy crater region in the eastern desert, contain lava tube features that have been documented in part, but not exhaustively. The relationship between the documented features and the full extent of the underground tube systems in these areas remains genuinely unknown. The sealed mine shafts of the Mojave present a different kind of underground mystery, one that sits at the intersection of human history and natural geology. Many of the abandoned mine shafts in the desert have been sealed by the Bureau of Land Management and other agencies as a public safety measure. Their openings closed with bat-friendly gates that prevent human entry while allowing the passage of bats and other cave-dwelling animals. This is appropriate and important work, but it also means that the underground worlds accessible through those shafts, worlds that may include both the human-made workings of the mining era and the natural geological features that those workings intersected, are no longer directly accessible for investigation. The historical mining records that might provide information about what those underground workings contained are, as we noted earlier, incomplete and inconsistent. Some mining operations maintained detailed records of their underground workings, producing maps and engineering drawings that survive in State Mining Bureau archives and historical collections. Others were smaller, more informal operations whose documentation, if it ever existed, has not survived. The gaps in the historical record mean that for many abandoned mine sites in the Mojave, the underground worlds accessible through those sealed shafts are simply unknown, their character, extent, and relationship to natural geological features undocumented. The climate record, preserved in desert cave formations, represents one of the more scientifically significant categories of what the Mojave still keeps hidden. The speleothems, the stalactites and stalagmites and cave flowstones that grew during wetter periods of the Mojave's past, are physical records of the conditions under which they formed. The chemistry of the minerals they contain, particularly the ratios of different isotopes of oxygen and carbon, encodes information about the temperature and precipitation conditions prevailing at the time the minerals were deposited. Speleothem paleoclimate research has been conducted at cave sites throughout the Southwest, and the results have significantly advanced understanding of how the region's climate has changed over the past several 100,000 years. But the coverage of this research in the Mojave specifically is uneven, reflecting the incomplete survey of cave resources in the region. Speleothems that have never been identified because the caves that contain them have never been entered represent a potentially significant archive of paleoclimate information that remains locked in the rock. The future archaeology of the Mojave Underground is another dimension of what remains hidden and what remains possible. Archaeological survey of cave and rock shelter sites in the desert has documented remarkable evidence of human occupation and use across thousands of years, but that survey is far from complete. Sites exist in areas that have not been systematically surveyed. Sites that have been identified have not always been fully excavated or analyzed. The relationship between the known archaeological record and the full extent of human use of underground and sheltered sites in the Mojave is, like so much else about this landscape, an open question rather than a settled answer. The underground water that continues to move through the Mojave's rock formations, the ancient groundwater that has been in the system since the wetter climates of the Pleistocene, represents both a scientific resource of considerable value and a conservation challenge of increasing urgency. As human populations in and around the Mojave Desert continue to grow and as climate change alters the precipitation patterns that recharge the aquifer systems, understanding the full extent and connectivity of the underground hydrological network becomes more important. Hydrogeological research in the region is ongoing, and each study contributes to a more complete understanding of how underground water moves through the desert. But the aquifer systems of the Mojave are deep, in some places extending to depths of hundreds of feet below the surface, and their full three-dimensional structure has not been mapped with anything approaching completeness. The interactions between surface hydrology, the springs and dry washes and seasonal drainages of the desert surface, and the deep groundwater systems below are complex and in many places poorly understood. Mystery survives in the Mojave not because the landscape is deliberately withholding, not because any human agency has chosen to restrict knowledge of what lies below, but because the desert is simply too large, too complex, and too demanding to yield its secrets quickly. The geological processes that built the underground Mojave operated on timescales of millions of years. The exploration and documentation of that underground world is operating on timescales of decades and centuries. There is no reason to expect that a landscape built across deep time will be comprehensively understood within any single human lifetime or any single generation of scientific effort. This is not a counsel of despair. It is, if understood correctly, one of the most compelling things about the Mojave Desert. It is a landscape that will reward sustained scientific attention for as long as that attention is directed toward it. Every generation of researchers will find new questions where the previous generation found answers. Every new technology will reveal features that previous technologies could not detect. Every cave that is surveyed will raise the possibility of additional caves beyond its mapped passages. The mystery of the underground Mojave is not a gap in our knowledge waiting to be filled and then set aside. It is a living frontier, as active and as productive as any research frontier in the natural sciences, generating new questions faster than existing questions are answered, revealing complexity at every scale from the microbial communities on cave walls to the deep aquifer systems that underlie entire mountain ranges. Future archaeology, future geology, future hydrology, future biology, all of these disciplines will continue to find the Mojave underground a productive and inexhaustible subject. The desert is large enough, old enough, and complex enough that this will remain true for generations to come. That perhaps more than any specific discovery or any particular mystery is what makes the underground Mojave genuinely extraordinary. It is not simply that it contains remarkable things, though it does. It is that it contains more remarkable things than any current inventory can capture. It is a landscape that exceeds our ability to fully know it, and that excess, that ongoing surplus of the unknown over the known, is precisely what keeps calling researchers and the curious and the simply attentive back to its surface and into its depths. The desert keeps its secrets not through concealment, but through sheer, patient magnitude. The sun reaches the western horizon of the Mojave in a particular way that is unlike any other desert sunset. It does not simply descend and disappear. It lingers. The atmosphere of the high desert, so dry and so clear of particulate matter most of the year, refracts the light of the declining sun through a spectrum of colors that moves slowly across the sky from east to west as the sun drops. The volcanic hills that were dark silhouettes before dawn are now amber and rose and a deep, warm ochre. The valley floor, which held no color at all in the pre-dawn darkness, is now painted in shades of gold and sienna that shift and deepen by the minute. And the wind, which has been building through the afternoon hours, begins to settle. It does not stop all at once. It diminishes gradually, gust by gust, until what remains is just the gentlest of movements across the desert floor, lifting a little sand here, bending a creosote branch there, passing through the Joshua trees with a sound so soft it is almost indistinguishable from silence. We have traveled a long way through this desert today, through time measured in millions of years and in individual human lifetimes, through rock and water and fire and the patient work of geological forces that operate below the threshold of human perception. Through the accumulated knowledge of peoples who understood this landscape long before anyone thought to map it, and through the fragmentary records of those who followed them with picks and lanterns and dreams of mineral wealth. It is worth pausing here in this golden late light to hold all of that together for a moment before the darkness comes. The stone beneath your feet in the Mojave Desert is not simply rock, it is a record. The basalt of the lava fields was molten within the past 10,000 years, and in some fields considerably more recently than that. The limestone of the Providence and New York mountains was deposited as marine sediment in a shallow sea that covered this region hundreds of millions of years ago. The fault scarps visible in the mountain ranges to the east and west are the surface expressions of tectonic forces that have been reshaping this landscape for 30 million years and have not yet finished. That record is not static. It continues to be written. The faults are still moving, in increments too small to feel in any given year, but accumulating over geological time into displacements of hundreds of feet. The underground water is still moving, still dissolving rock grain by grain, still depositing minerals in cave chambers that no light has yet entered. The volcanic fields of the Mojave are not extinct. They are dormant, which is a different thing entirely. The magma that fed the Cima volcanic field's most recent eruptions may still exist at depth, cooled and solidified for now, but connected to a system that has produced eruptions within human prehistory and may produce them again. The water that carved and shaped the underground Mojave left its deepest marks during the wetter climates of the Pleistocene, but it has not finished its work. Somewhere beneath the desert floor right now, fossil water that fell as rain during the last ice age is moving through aquifer rock toward a discharge point that may be miles away and centuries in the future. The springs that emerge at the base of desert ranges are fed partly by this ancient water, and the caves that water shaped on its long journey through the rock still hold the formations it deposited as evidence of its passage: water and stone. These are the primary materials of the underground Mojave. They work together at timescales that dwarf everything else in this story: all the human history, all the archaeology, all the mining and the exploring and the mapping. Water and stone were shaping the underground world of the Mojave long before any human being arrived here, and they will continue doing so long after the last human presence in the desert has been covered by sand. The human perseverance that this landscape called forth across its history deserves its own acknowledgement in this final light. The Paleo-Indian hunters who crossed the Mojave 13,000 years ago, navigating by stars and landscape memory between water sources, were doing something genuinely extraordinary. The indigenous peoples who built their lives in and around this desert across the subsequent millennia, developing the deep ecological and cultural knowledge that allowed them to thrive in one of North America's most demanding environments, demonstrated a form of human adaptability that is remarkable by any measure. The prospectors and miners of the 19th century, whatever the complicated legacy of the mining era, were also people of considerable toughness and determination. They carried their equipment into some of the most remote and hostile terrain on the continent, sank shafts into hard rock by hand, built camps and communities in places where water had to be hauled for miles, and persisted through conditions that would defeat most modern people within days. They found things, they lost things. They left behind a landscape studded with the physical evidence of their effort, the abandoned shafts and rusted machinery and half-collapsed headframes that still stand in the desert today as monuments to human ambition and human limitation. The researchers and cave explorers who work in the Mojave today carry a different kind of determination. It is quieter, more methodical, less immediately dramatic than the prospectors' work. But the patience required to conduct systematic cave surveys in an environment this demanding, the care required to document underground features accurately, the scientific rigor required to distinguish what is known from what is merely suspected. These are also forms of human perseverance worth recognizing. Indigenous memory of this landscape is not a thing of the past. The Mojave people, the Chemehuevi, the Southern Paiute, the Serrano, the Cahuilla, and the other nations whose ancestral territories include parts of the Mojave Desert are not historical figures. They are present-day communities maintaining living relationships with a landscape their ancestors inhabited for millennia. Their knowledge of the desert, encoded in language and story and cultural practice, represents a form of understanding that continues to have relevance and value, not as a romanticized echo of the past, but as a living body of knowledge about a living landscape. The conversation between indigenous knowledge, historical documentation, and modern science about what the Mojave is and what it contains is ongoing, and it is richer for including all of those voices. No single framework captures the full complexity of a landscape this old, this large, and this layered with meaning. Geological time has a way of reorienting the human sense of scale. Standing in the Mojave at dusk, watching the colors change in the western sky, it is possible to feel, briefly, the weight of all the time that has accumulated in the rock beneath your feet. The millions of years of volcanic activity and tectonic movement and water working through stone. The hundreds of thousands of years of alternating wet and dry climates writing their record in cave formations and lake sediments. The 13,000 years of human presence, itself a vast span of time by any ordinary measure, but a relatively recent development against the geological background. That sense of deep time is not diminishing. It is not depressing or alienating or an occasion for existential unease. It is, when received quietly and without resistance, something more like peace, an invitation to understand yourself as part of something very much larger than any individual life or any particular historical moment. To recognize that the desert was here before you and will be here long after, and that this continuity is not a rebuke but a context. A reminder that the things that endure in this landscape are not the things built quickly, but the things built slowly, by water and stone and time and patient biological adaptation. The cool air is rising again from the fissure in the rock at the base of the volcanic hill. The temperature on the desert surface is dropping as the last light fades, but the air coming from below is the same temperature. It has always been the same temperature. It will be tomorrow morning, and next year, and 100 years from now. Because the underground does not experience the surface fluctuations, it exists at its own thermal constant, its own pace, its own deep and patient time. The wind moves gently across the desert floor, lifting a little sand, settling it somewhere else. The first stars appear above the eastern horizon, the same stars that rose above this desert last night and 10,000 nights before that, indifferent to the specifics of any single evening, but providing, as they always have, a fixed reference for those who know how to read them. Below the desert floor, in cool passages and chambers that no light has yet reached, water moves through stone in amounts too small to hear. Mineral formations grow in fractions of millimeters. Bats hang in clusters in the darkness, breathing slowly, their heart rates measured in beats per minute rather than per second, their lives adapted to a world of constant conditions and careful energy management. The desert does not end at its surface. It descends through volcanic rock and fractured limestone and ancient sediment and deep aquifer stone, into a world that is genuinely its own, governed by different rules, shaped by different forces, operating on different timescales. A world that human beings have barely begun to understand, and that will reward patient attention for as long as anyone is willing to bring it. The Mojave keeps its underground world not through any act of concealment, but through the simple, overwhelming fact of its own magnitude. The desert is too large, too old, and too complex to yield everything at once. It offers what it offers slowly, piece by piece, to those patient and careful and humble enough to receive it. The stars are fully out now. The desert is quiet. Somewhere below, cool air moves through stone in the dark, and the Mojave, as it has always done, continues.